everyone to today's Wednesday seminar. Today we have George Guice, as I have told, George Guice from Smithsonian Mineral Science Museum. And he will talk about, as you can see on the screen, the Baltimore Mafic Complex. Let's welcome him and learn from him.
Thanks very much. Grace, thanks for that. Hey everyone. Thanks for coming along today. Hope that you're all doing pretty well, particularly given the circumstances. And yeah, as Grace mentioned, I'm going to be talking today about these highly altered dark rock on our doorstep in Maryland, so the Baltimore Mafic Complex. And we'll be discussing these rocks in the context of the Appalachians, so formation of the Appalachians, which, as you all know, runs from Alabama up to Newfoundland in Canada. And this project started shortly after I moved to DC back in June 2019. I was to start a postdoc, as mentioned, at the Smithsonian with Mike Ackerson. And sort of additional to the main thrust of the research, I was quite keen to get involved and study some local rocks. And after a bit of reading, chatting with Mike, I learned about these nice altered rocks in and around Baltimore. And from there, it kind of snowballed. You can see we've got quite a big team here that's been involved in putting this together, which are on the call, which is nice, and hopefully we've got a pretty interesting story for you. As the title suggests, we think that the Baltimore Mafic Complex, or BMC for short, represents various ophiolite fragments. So I'll be keen to hear what you think and whether or not you agree with our findings. And before I sort of crack on with discussing the BMC, I'm just going to quickly give you an introduction into the kind of research that I spend most of my time doing. I'm not looking at these dark rocks in Maryland. Generally speaking, I've spent most of the last 5 years looking at Archean age rocks, so those between 4 to 2.5 billion years old, and a variety of locations you can see here. And the types of rocks that I generally look at are ultramafic and mafic rocks. So these started their lives as quite magnesium-rich igneous rocks that, like the BMC, have been really quite heavily affected by secondary processes. So they've been really deformed, really metamorphosed, and heavily altered. And essentially, what I've been trying to do is constrain the effects of these secondary processes and try to understand something about the origin of the rocks. So ultimately, what we want to do is contribute to our understanding of these large-scale geodynamic processes that operated during the Archean. The obvious question is, well, why? Why are we interested in studying these old, dark, altered rocks? And I know there are several people in the department at UMD who are pretty interested in this research area. So I'm probably going over well-trodden ground here. But ultimately, we don't know, or maybe more accurately, we can't agree, how the Earth worked during the Archean. So this debate is commonly articulated around that question: when did plate tectonics start? Some people would say we've had it since 4.2 billion years ago. Others that we didn't have it until 0.85 billion years ago. And clearly a whole bunch of suggestions in between. Now, clearly all of these suggestions implications for the nature of Earth's geodynamic mode during the Archean. And if we believe these early onset predictions, then the majority of rocks we see on Earth are tectonic processes. If we believe these late suggestions, then something else was going on. And sort of an alternative view, something that's been gaining a lot of traction in the last 5 years or so, is that perhaps we had a fundamental shift in and around 3 billion years ago, meaning that the early Archean rocks formed in a different geodynamic regime, and the late Archean rocks formed in a plate tectonic regime. So it might seem kind of counterintuitive, as I've spent the first few minutes of a talk about 0.5 billion-year-old rocks, talking about 3 billion-year-old rocks. But I do think there's a kind of interesting tangential link here that we can circle back to at the end of the talk. So just a final bit of housekeeping then, before we crack on with the main thrust of it. You're going to hear a lot of talk about ophiolites and layered intrusions. So for those of you who don't spend your working lives thinking about these things, what am I talking about? Well, ophiolites are essentially oceanic lithosphere, so the crust that underlies the oceans, along with the uppermost mantle, that have been thrust onto or into continental lithosphere. If those continents are then eroded down to the right level, then we can walk on oceanic lithosphere or ophiolites and examine them. Layered intrusions, on the other hand, are essentially fossil magma chambers. So they're generally sill-shaped, a little cartoon here. And in the context of this study, any magmas that go on to form layered intrusions would likely be associated with a subduction zone. You can see in this little sketch here. And so essentially, clearly, if we're looking at a portion of Earth's lithosphere and we apply one of these two interpretations to a suite of rocks, then we are placing very different constraints on the evolution of that lithosphere. So if we had formation in an oceanic environment with faulting into place, those very different suite of magmatic and tectonic processes required in comparison to sort of an intrusion of a magma in situ. So that's the housekeeping out of the way, and now we can travel a couple of thousand kilometers northeast of us in the Maryland area up to Newfoundland. And what we'll find there is a really well-exposed suite of ultramafic to mafic bodies, as you can see in this beautiful example. Many of these bodies have been interpreted as ophiolites. So if we take a look at a simple geologic map of Newfoundland, you can see ophiolitic rocks here in the black colours are distributed throughout the island. And also, if we sort of zoom in on an area on the north coast, we can again see quite a lot of ophiolitic rocks. And as I just mentioned, these ophiolite hypotheses place quite an important constraint on the magmatic and tectonic evolution of the northernmost Appalachians. Now I'm going to contrast that with the central and southern Appalachians. We have a bunch of ultramafic and mafic bodies, some of which I've marked here on the map, but the exposure is considerably poorer. The rocks, as you can see here, are highly altered, highly weathered, so we don't have these beautiful exposures that I showed you from Newfoundland, and instead we sort of have to make do, I guess, with these often floor exposures. And what that means is that the origin and the magmatic affinity of these bodies is much more ambiguous. And we don't have that constraint on the magmatic evolution of the central and the southern Appalachians that we have in the north. So as I mentioned, our focus here is on the Baltimore Mafic Complex. I hope you all know roughly where that is in a big picture context. And the BMC is discontinuously exposed throughout Maryland and southern Pennsylvania. This simplified map shows the approximate extent of the ultramafic and mafic rocks, but it does sort of overemphasize how continuous they are. In reality, they're a bit more discontinuous than this. So we're dealing with a late Cambrian crystallization age, about 490 MA, with the metamorphism dated at 450 MA. And like everything in this area, the contacts between the ultramafic and the mafic bodies and the surrounding metasediments are poorly exposed. When we do see them, they seem to be tectonic. So we're going to focus today just on the southern part of the BMC, which is exposed in and around Baltimore. So you can get a slightly better impression of how discontinuous the exposures are from this slightly more detailed map. As I alluded to earlier, there have been a variety of interpretations that have been applied to the BMC. So some have suggested that we're dealing with various ophiolite fragments, others that it's a stratiform layered intrusion associated either with a continental volcanic arc or a back arc basin. So what I'm going to try and do here is break this question down into two parts. So first we'll ask that more simple question, is it an ophiolite or is it an intrusion? And then we'll try and expand on that and ask, can we be more specific about the magmatic affinity of the BMC? So how have we gone about attempting to answer these questions? Well, first and foremost, we collected 19 samples of ultramafic rock from 3 different ultramafic bodies in the area. Please note that we're only focusing on ultramafic rocks in this study. We're not looking at the mafic rocks. So we've got 5 samples from Ultramafic located up in the northwest, 2 from Bear Hills in the north, and the remaining 12 samples are from the Hollofield Ultramafite. And this is the largest body here in the area. Within that, there are 3 localities, the majority of which are from this Hollofield quarry area, sort of old, overgrown, abandoned quarry with some reasonably good exposures. So for each of these samples, we've done sort of the basic petrography, and we've also collected major trace element bulk rock geochemical data and spinel mineral chemistry as well. So I'll give you a little bit of field context and petrographic context here, starting with these 2 smaller bodies, Soldier's Delight and Bear Hills. Now, both of these localities form generally massive, highly altered outcrops. Perhaps if you kind of squint at this outcrop and see it in the right light, there may be some layering, but otherwise, as I say, we're dealing with massive, highly altered rocks. You can see that alteration in the thin sections quite clearly. We're looking pretty much just at serpentine and amphibole as our dominant minerals. There are some opaque phases in here as well. These are spinel grains. They're quite sizable, as you can see. In this case, 500 microns or so in diameter, but sometimes they're bigger. Moving on then to the Hollofield Ultramafite, so this larger body, we do see some small remnants of olivine and of pyroxene in places, but as with Soldier-to-Light and Bear Hills, serpentine and amphibole are the dominant minerals. And there's the variation in serpentine and amphibole does result in quite a distinctive layering. We can see that layering on a variety of scales. So here we can see it on the millimeter and the centimeter scale. We can also see this layering on a sort of decimeter and meter scale, as you can see from this log that Joe and I did back in August of 2019. So you can see from this that there are some subordinate mafic rocks as well. Got some metagabbro, some anorthosite, garnet metagabbro, and there's a chlorite garnet schist in here as well. But predominantly we have ultramafic rocks, so what we're calling metaperidotites, metaperoxenites, those serpentine and amphibole dominant lithologies. So what that context tells us is that these rocks have been highly altered and that the chemical data is therefore very likely to have been affected by secondary processes, both in terms of the bulk rock data and the spinel data. So because we're interested in the primary origin, we need to sort of try and constrain any secondary effects before we go and interpret the data. So we'll start with the bulk rock data, and one way of testing the mobility of a specific element is to take a large number of samples that are definitely cogenetic and where we have a lot of contextual information, and to establish the correlation with a highly immobile element like ytterbium or zirconium or yttrium. Now, for the reasons I've already described, this method is not really possible here. We're dealing with really poor exposures, a real absence of contextual information. So I think that the best we can do is utilize these 8 samples from the Hollofield quarry. They are from continuous exposure, and we know that they are cogenetic, and from the log that you saw, we have a reasonable amount of contextual information. So clearly 8 samples is not statistically robust, so I just want to emphasize that we need to treat this as an indication in the absence of all the factors that we ideally need, but it's the best we can do given the scenario. So using this method, we can see that some elements like yttrium, zirconium, samarium, and heavier earths like holmium have very strong correlations with ytterbium. You can see that expressed by the R² values up here. And what this suggests is that these elements were relatively immobile during all of this alteration that the rocks have experienced. Now contrast that with elements like rubidium, and barium, and thorium, and some of the light rare earths as well, like lanthanum. And we see really poor correlations here. Again, you see that in the R-squared values. And it's therefore likely that these elements have experienced some mobility during all of this alteration. And what that means for us is that there are some elements that we really sort of shouldn't trust too much when we're trying to interpret the origin of the BMC. So what I'm going to do in future plots is highlight any element that shows these poor correlations. I'll highlight them in red, just to sort of urge caution for them. And as I say, just to kind of reiterate, this is only an indication based on a relatively small data set, but it does give us a kind of reasonable approximation. Things, I think, are a little easier when it comes to the spinel mineral chemistry. So you can see from this BSE image, backscatter electron image, some of these spinels are distinctly zoned, so that the rims are really iron-rich, chromium and aluminum poor, while the cores are the opposite, so they're iron poor and chromium and aluminum rich. And as you can see from the element map, the core compositions are pretty homogeneous. They form quite tight compositional groups down here on bivariate or ternary plots. The rim compositions, on the other hand, show a significant variation from towards the core to towards the rim. So you can see on this iron map, for example, the iron abundances decrease towards the center of the rim. So, for example, here is the number 2 towards the center of the rim. They plot here on the bivariate plot much closer to this core composition, and number 3, which is clearly closer to the edge of the grain, plots further away from these core compositions. So as you would expect, we interpret these cores as representing primary compositions and the rims representing various secondary compositions. Now, there is another group of spinel grains that don't really show the distinctive zoning in the BSE images, but they do show from core to rim the same chemical change that I described for the rims on the previous slide. So as we move towards the edge of the grain from number 4 to number 5 to number 6, there is an increase in the iron concentrations and a decrease in the chromium and the aluminum. So again, you can see that progression on the chemical plots. So there's sort of 2 options here. Both could actually be true. Option 1, these grains like this have been pretty much entirely affected by secondary processes, barring this tiny little bit in the middle here. Or alternatively, we have a grain and we have sliced essentially through the side of that grain in the thin sectioning process. And it's an artifact of thin sectioning. Like I say, could be a mixture of the 2. So with that then, let's move on to one of the 2 key interpretations that I think we can make using these data. I'm going to first focus on the Soldier's Delight locality, located up here in the northwest of the study area, because I sort of think that's where the most important and interesting results come from. We'll start just with the simple major element chemistry. And what we can see here is that the Soldier's Delight samples, so those in blue here, are really quite magnesium rich. And they overlap with this grey field, which is a field for oceanic residue or mantle rocks. Now,
On its own, this doesn't tell us too much, because these major element compositions could just be the product of sort of really olivine-rich cumulates. But I think they're particularly interesting when you combine that with the trace element chemistry. So again, the first thing to point out here is that I've highlighted these elements that show poor correlations with the terbium in red. And we'll treat these elements with sort of pinch of salt. At the other end of the plot, this more compatible end of the spectrum, and these elements that we think are more immobile, you can see a really significant overlap with this field for residual mantle rocks here in grey. The crucial thing really is that these rocks are just exceptionally depleted in trace elements. So for people not familiar with why that is significant, when you partially melt the mantle, trace elements are concentrated into the melt that ascends towards the surface, meaning that the residue, so that the mantle that is left behind, is depleted in those elements, producing compositions that look something like this. So in terms of the bulk rock chemistry, it seems that this Soldier's Delight locality represents a bit of mantle here in central Appalachians, pretty close to where I assume a lot of us are sat at this very moment. And this hypothesis is also consistent with the spinel mineral chemistry. So I've just picked out a couple of key plots here. The grey analyses are those secondary compositions that I pointed out earlier. And what you'll see is that the primary spinel compositions from Soldier's Delight, again in blue, overlap with the sort of mantle peridotite field on both of these plots. So the first key finding then here, sort of in answer to that first part of the question that I posed at the start, ophiolite or layered intrusion, is that the BMC probably represents various ophiolite fragments, and that Soldier's Delight probably forms a part of the mantle section. The next question really would be, how do the other localities fit in with that hypothesis? So moving on then to this largest body, the Hollofield Ultramafite, located here in the center of the study area, there are several key differences to the Soldier's Delight rocks. So first, field geology. We can see this distinctive layering that I described earlier on a variety of scales, and this is something we don't see at those Soldier's Delights, that Soldier's Delight locality. Second, major element bulk rock geochemistry. These rocks are much more evolved. Their MgO contents are still quite high. They're still ultramafic rocks, but they're significantly lower than for the Soldier's Delight rocks. And third, in terms of the trace element bulk rock data, there isn't that overlap with the mantle field we saw a moment ago. These rocks sit in and around 1 on the primitive mantle normalized plots. And all of this is much more consistent with crystallization from a melt rather than these rocks representing residual mantle like we're suggesting for Soldier's Delight. Now, unfortunately, there aren't any spinel compositions that we can be confident are primary from this locality. The spinels are much smaller and they appear to have been completely altered, and as a result we sort of don't have that line of evidence to add in here, unfortunately. Now, despite that, if we sort of accept the ophiolite premise for these rocks, it then seems quite likely that a Hollofield Ultramafite represents sort of this layered ultramafics part of an ophiolite that many people interpret as representative of the moho. And what about our final locality then, the smallest locality at Bear Hills up here? Well, things here are a little bit more ambiguous. The trace element bulk rock geochemistry is similar to the Hollofield quarry and the Hollofield Ultramafite more broadly, showing those relatively enriched patterns. But the major element bulk rock geochemistry and the spinel mineral chemistry are both much more similar to Soldier's Delight. And the field geology is also quite ambiguous. We have that sort of possible layering at that locality if you looked in the right light, but I would probably lean towards it being more similar to Soldier's Delight on this as well in terms of the field geology. So I think we should certainly include a question mark here over the origin of Bear Hills. If you pushed me, I would probably lean towards a mantle origin. Perhaps we could explain the trace element geochemistry by interaction with mantle melts that would have the effect of sort of refertilizing the mantle, re-enriching it in trace elements. But ultimately, I don't know, is the simple answer. So I hope I've convinced you that we could at least be looking at fragments of an ophiolite right here on our doorstep in the DC, Maryland area. And what I want to do now is try to take this one step further and explore sort of the specific magmatic affinity of the BMC. Now, to do that, I've compared that Soldier's Delight bulk rock data, so the rocks that we think are representative of mantle rocks. I've compared that to more specific global data sets. So we have abyssal serpentinites, which are oceanic mantle rocks formed at slow spreading ridges, and we can use as a proxy for mid-ocean ridge type ophiolites. And we also have mantle wedge serpentinites, which are mantle rocks formed for in and around convergent margins. And we can use as a proxy for suprasubduction zone ophiolites. Ultimately, the simple question here is, are we looking at oceanic lithosphere formed A, in the middle of an ocean, in association with sleeve force spreading, or in a convergent margin right next to a continent? So there's a reasonable overlap with both of these fields. But I think the key difference comes in terms of the elements at the more compatible end of the spectrum. These are the elements, again, that we think are the most immobile. So whereas the abyssal serpentinites have this sort of strong positive slope that you can see here between approximately gadolinium and lutetium, that isn't really something that we see in the Soldier's Delight data. They seem, the Soldier's Delight data, to resemble more the mantle wedge serpentinites. So they're more flat or mildly sloping patterns between approximately gadolinium and lutetium. So that's what tentatively suggests that maybe we're dealing more with this second option, the suprasubduction zone type ophiolite, rather than formation in association with seafloor spreading. And this hypothesis is consistent with the primary spinel compositions, which overlap much more with the suprasubduction zone peridotite field rather than the more peridotite field. So I think with that, our second key finding, I'd say more tentative than the first, is that the BMC likely has a suprasubduction zone ophiolite affiliation, meaning that possibly we have suprasubduction zone ophiolites both in Newfoundland and also in Maryland. So I don't think we should overinterpret the results of this study. We're just looking at some scrappy exposures in Maryland, but I do think that it raises some interesting questions about the evolution of the Appalachian Orogen. So are these ophiolites in Newfoundland and Baltimore sort of along strike equivalents, separated by thousands of kilometers? If they are, what is causing the differences between the two? Was it something fundamental in the formation of the oceanic lithosphere and the obduction, the emplacement of the ophiolites? Or alternatively, are the differences sort of much more local? Do they owe their origin to the unique tectonic, hydrothermal, metamorphic processes that have affected these rocks in their sort of 490 million year history? And also potentially it helps our understanding of the temporal evolution of the central and southern Appalachians. As I mentioned at the start, this has the potential to place an important constraint on the magmatic and tectonic evolution of this portion of the Orogen. So what next is the question. Well, I think it would be prudent to test this hypothesis further, and we plan to do that in two ways. So first we'll ask, is this hypothesis consistent with the northern part of the BMC? Remember, we're only focusing here on the southern part. So I've collected a bunch of samples from the state line area around the Susquehanna River, along with Jerry Burgess and Wendy Nelson. And we plan to start to take a look at those more closely pretty soon. The second avenue here is to focus on the chromatite mineralization. Now, chromatite mineralization occurs both in the south and in the north of the BMC. And additional to examining the chromite itself, we're also interested in the platinum group minerals associated with that chromite. The reason for doing that is because the platinum group mineral assemblage associated with chromatite in mantle rocks, so known as podiform chromatites, are relatively distinct from the platinum group mineral assemblage associated with chromite in lead intrusions, known as stratiform chromatites. So if you guys at UMD are interested in getting involved, have some ideas, have some thoughts, comments, I'd be really quite happy to chat about that. So that'd be great. And finally, before I wrap up, I said at the very start of this talk that this research was tangentially related to my work focusing on similarly altered, similarly metamorphosed Archean rocks. And I think it is worth mentioning that confidently identified ophiolites become much more sparse the further back we go through Earth history. So there are a lot of confidently recognized ophiolites in the Phanerozoic. There are a few in the Proterozoic, but as we go further back, and particularly when we get into the Archean, those proposed, and there have been quite a few, are much more controversial. And one thing that we seem to be lacking, as far as I'm aware, is the mantle rocks. And of course, as I've shown here, that seems to represent the kind of most distinctive part of any ophiolite. Now, clearly, it makes sense that these will be more difficult to recognize the further back we go. They're increasingly affected by alteration and metamorphism and deformation. But I guess my intentionally sort of thought-provoking question here is, if we had plate tectonics as far back as some of these suggestions, why is it sort of so difficult to identify mantle in the Archean? And we've shown in this study that exceptionally poorly exposed, highly altered, albeit much younger, rocks can be quite convincingly shown to be mantle, at least in my opinion. And that sort of gives me hope that if Archean mantle is out there as part of an ophiolite, then perhaps we might be able to find it using the workflow and the methodologies that we've shown here. Maybe we'll be able to use that in some way to contribute to this big discussion that I outlined at the start. With that, I'll just leave you with the conclusions on the screen. Thank you very much for listening. Please feel free to provide feedback, ask questions, completely disagree with everything that I've just said, if you like, whether that's now or via email at a later date. So yeah, I'd be delighted to discuss. And again, thanks for having me, and thank you for listening.
Thank you, George. This is great. Do we have any question from the audience? I guess your presentation is very good. Oh, Rich Walker. I have one question from Rich Walker, or multiple questions. You can unmute.
I think I'm unmuted. Can you hear me?
Yes.
George, really nice talk. You've visited some locales that we've been to in the past. You've been to some that I've never been to. Do you have GPS coordinates for where your different samples come from?
Oh, absolutely, yeah. I actually meant to say that at the end. If people are interested in going and checking out these localities, I'd be delighted to share all of our GPS coordinates so that people can go and take a look. The exposures that you've seen are quite underwhelming, but people are interested getting some samples themselves, taking a look, for sure.
Uh-huh.
I'll send them across.
Is Wendy Nelson planning to do any PGEs on these?
She might be. I'm not sure. Yeah, we're kind of, so we collected the samples about a month ago, and we're sort of discussing what to do with them now. I've crushed them and got them cut for thin sectioning, and the next steps are kind of in discussion, depending on various lab, availabilities and things like that.
Yeah, we've done some PGE work off and on over the last 25 years. I guess most of our local focus was on chromatites from Nottingham, which is across the state line up in Pennsylvania.
Mm-hmm.
But I don't think we've ever put the data together in the way that you're envisioning. So might be interesting.
For sure. Thanks.
Okay, Phil has one question. Phil, you can go ahead.
What if I have two? George, I enjoyed that very much. Thanks very much for doing that. The history of performing geology in this area, it goes on for over 100 years. And I was looking at an old state geologic map and noticed that the map that you use actually has quite a bit more detail. And I was wondering, where did you get the base map that you showed us repeatedly?
So that was from a sort of collaborator of mine, Will Junkin, at the Maryland Geologic Survey. And he sent me the various base maps. And Will is actually redoing the quadrangle for the BMC area at the moment, or he was in pre-COVID times, and maybe he's getting around to finishing it now. So yeah, I got them from Will, and then traced the various maps and sort of amalgamated them all together.
That's quite nice.
Again,
Some of the some of the problems that exist on the state map and the old quadrangles don't exist on that. And I just noted that it was very different. Now I'm going to ask a question, another question. One of the things that Drake talked about in the Piney Branch ophiolite further south across the border was the presence of plagiogranites. And in fact, across the Henry Nice Bridge, south of Waldorf, there's supposed to be a large plagiogranite body.
Okay.
Have you observed any plagiogranite dikes in any of these ultramafic complexes? How extensive are they, if they exist? And what do they tell us?
Yeah, Joe and Jerry, actually, who are on the call, might want to come in on this as well. I know Naomi Becker is a PhD student working with Daniel Viette at Hopkins, and she's kind of interested in these plagiogranites. I think we've seen some in the BMC in Maryland at one locality. It was kind of up a treacherous walk up a creek. Again, I can dig out coordinates and stuff if you're interested. But yeah, Joe and Jerry might want to come and add in because they have seen lots of the local geology, even more than me. Maybe not.
If I'm recalling which one you're talking about, it was down in the Relay area in the Sapsco Park.
That's right, yeah.
Yeah, and on, yes, name dropping Naomi, she's actually curious about these plagiogranites. She's looking at Ophiolite in Norway and kind of understanding the formation of the plagiogranites there. And that brings a curiosity to the Baltimore area. I wish she was on the discussion right here because she has a lot more to say about it than I do. But I'm sure she'd be happy to answer some questions if anybody wanted to reach out to her.
Yeah, I think Naomi's particularly interested in these because they seem to be used to date ophiolites, and she's interested in what the origin of these plagiogranites are, whether they're potentially partial melt products or whether they're fractional crystallization products. And clearly, understanding that origin has implications for whether that using those to date the timing of the formation is useful.
Thank you.
We still have time. Do we have other questions?
I'll ask another question then. Have you looked at any of the mafic rocks further south, southeast of Columbia? Any thoughts on?
I have not myself, unfortunately. Yeah, but again, I know that Naomi has, and she's actually been down to Alabama to look at the Daneville complex down there. But yeah, I have not.
I'm talking Columbia, Maryland, not South Carolina.
Oh, Columbia, Maryland. No, not myself. No.
Okay, one last time. If there's no more questions, then I will say thank you, George, for giving us this amazing presentation. And if you guys have more questions, please reach out to him. And then his email is listed on the screen right now. So very easy to contact.
Yeah, please feel free. And thanks again for having me, everyone. I appreciate it.
And then follow his Twitter.
Sure.
Thank you.